Yeah, no, this is not a hard chapter. Okay, so this is chapter 12, heat, temperature, and calorimetry. Um, so the first thing is temperature, and temperature is literally a measurement of how fast particles are moving, but we don't usually talk about it that way. We think about it as like how warm something feels. But it's literally a measurement of how fast the molecules are moving. Um, and so with Celsius, 100 degrees is water boiling, 0 is water freezes. This dude named Andrews Celsius invented Celsius in 1742. So we needed a way of talking about how warm something was. When I say that the molecules are moving in a liquid or in a gas, the actual molecules are going to move around. When we're talking about a solid, it's going to have a crystalline structure in that the molecules might not move like relative to one another, but you can have these things happening. So it can wiggle, like the little hands are going away from each other, or jiggling, or twisting a little bit. Like you can move without moving your feet when you're standing still. Does that make sense? So when we're talking about like a liquid or solid, or sorry, when we're talking about a liquid or gas, you can walk around the room. With a solid, you cannot move your feet, but you can move your arms and your body. So think about all the things you can do standing up. You can twist side to side, you can do jumping jack arms, you can lift weights, all those things that you can do. That's what's happening in a solid. And so we're like, okay, well, 0 freezing then is not actually 0 temperature because you still have some energy because you're able to move. So when we do physics equations, we have to use Kelvin because Kelvin is going to have a 0 where nothing is moving at all anymore. So at 0 degrees Celsius, there's a crystal structure. The atoms themselves are not moving around, but there is still movement. A 0 Kelvin, nothing moves at all. So for temperature in Kelvin, 0 degrees, all molecules are completely stopped moving. 273 Kelvin is the equivalent of 0 degrees Celsius. And 1 degree Celsius change is exactly the same amount as 1 Kelvin degree change. So if you're looking at the change in temperature, you can go from 273 to 293, and that's 20 degrees. Or you can go from 0 to 20, and that's also 20 degrees. So with a lot of these equations that we're going to be looking at, you're looking at the change in temperature. And as long as you're either in Celsius or in Kelvin, it doesn't matter because 20 is 20. Does that make sense? So in 1848, Lord Kelvin created the Kelvin scale of Kelvin. So yes, they're naming stuff after themselves. So just looking at this to go from 0 to 100, it's the same as going from 273 to 373. It doesn't matter. Fahrenheit is the one that's funky. Good job, United States and England. So 100 degrees Celsius is actually 212 degrees Fahrenheit. The way that this temperature scale, the idea was how did they pick 100 and 0 for Fahrenheit? Well, 100-ish was supposed to be body temperature, but they weren't very good measuring it yet. And 0 was supposed to be the coldest you could get water using salt and ice. So if you want to make ice cream, 0 degrees Fahrenheit is the coldest you can do it with rock salt, water, and ice. I know, super random. So Fahrenheit, if you were curious, the important things for Fahrenheit is making ice cream and body temperature. Celsius, it's water freezes and water boils. So there you go. Conversions. These are the equations you need. They are things you will want to write down and add to your equation sheet if they're not already there. And I'll put this in your Google Classroom so you guys don't have to copy everything at this exact moment. Or you could take a picture or whatever. Not hard. Equations number 1 and 2. Okay. Thermal expansion. Okay, you know the idea of like hot stuff gets bigger. Okay. That is this. So thermal expansions, the objects are going to get longer and they'll get wider as they get hotter. Gases will also expand. So if I want to know how much longer something gets, I use the change in length is equal to alpha, which is the coefficient of linear expansion. There's a list of them on page 321. The original length and the change in temperature. Again, you could do a change in temperature of Celsius or in Kelvin because they're the same. So, again, not hard. Good? Okay. So some thermal expansion examples. If you ever drive out like past Paso, you'll notice that there's a whole bunch of pipelines out there where the oil rigs and oil drilling is up there. You will see pipes go like this a lot. Some of them are much smaller than this, but the idea is you need to be able to let them get really cold in the winter and not break. You need to be able to have them get really hot in the summer and not break. And when some of the pipes have hot steam going through them, you need to have it be able to get really hot when you have hot steam go through it. And then in the winter, when you might not use that pipe anymore, you need it to be able to get cold and not break. So by doing this, the pipes are allowed to flex. As it gets really long, the parts in the bottom here can move towards each other, and the parts in the bottom can like go away from each other, and it won't break. And then if it gets cold and you need more pipe, it can bend out. These things are really cool. I'll get them out when I have my propane torch out, so you can see the ring and the ball, and how the two sizes change when one gets hot relative to the other. Bridges, you'll notice that there's weird gaps in things, because the bridges themselves will get longer when it's hotter, and the bridge itself will get shorter when it's colder, and you don't want the bridge to break. So when you design bridges, you will notice that there are gaps on either side of the bridge. Sometimes they're filled with like a squishy, like rubbery stuff. But the reason is in the summer, those gaps get smaller because the bridge itself is bigger. And in the winter, the bridge gets smaller, and so you need something to fill that hole. Or you have something like this so nothing falls in it. Train tracks will also have gaps. If you don't, what happens is in the summer when the tracks get long, they need somewhere to go. And so they smash into each other and then they bend. In the winter, they'll separate from each other because they're shorter. In the Upper Sierras, if you ever take the train from like San Jose to Denver, when it's really hot, they have the trains have to go much slower because of the potential waviness of the tracks. And they can't if you drive really fast over train tracks, you have more friction. The tracks will heat up, you get extra expansion. It causes all kinds of problems for the trains. So there's extra speed limits for some train tracks based on the temperature that it is, so that you don't have derailments and the train tracks themselves don't get messed up. So kind of cool. When we talk about thermal expansion of water, water is also going to expand when it is hotter. And if you take the same amount of liquid or gas and you make it hotter, it's going to expand. Now it's bigger. Okay, well, if you have the same amount of mass but a bigger volume, that means it's less dense. Something that's less dense will float. Just like we were talking about with the last unit. So hot air balloons, you get the gas hot, now it's less dense. Anything that doesn't fit just comes out the hole in the bottom, and then it'll float. Normal old-time water heaters are filled with water. Cold water is more dense. It sinks to the bottom. That's where you have the flame to heat up your water in your water tank. Then as the water gets hot, it's less dense, it goes to the top. The same thing is going to happen in your house. You turn on the heater. If you ever notice, the heater vents are at the floor. The reason is because then the hot air, as it goes up, is going to warm up the cold air, and then it's going to come back down when it gets colder. One thing you'll notice is that air intakes, where they are in the house, is actually kind of supposed to be strategic, although whoever designed my house wasn't thinking. Because my air intake is on the floor. So like in the summer, the cold air comes out at the floor and then gets sucked in at the floor. So the warm air that's up at the top of my house, like at the ceiling, like, no, that never gets cold. Like, kind of, because, the air will mix around a little bit on its own, but it doesn't work as well as if the air intake was up higher. So my house is great for warming in the winter, but awful for cooling it off in the summer. Okay, the most important thing about thermal expansion of water is that water does something weird, really weird. The most dense that water is at 4 degrees Celsius. 0 degrees Celsius is when it turns to ice. Now, what that means is that with most materials, the colder it gets, the more dense it gets, all the way forever. Water is funky. It's like, oh, actually, at a certain point, I'm going to get less dense when I turn into an ice cube. Okay? That is really super important and cool because, first of all, that means that ice floats. Second of all, it means that the fish get to live during the winter. So once the water gets 4 degrees, like once the whole thing is 4 degrees, then the coldest water will be the 4 degree water is the most dense. It goes to the bottom. And then it has to cool from the top down. But you're not going to have any of the water going around like this, like we did with the water heater, because the densest water is 4 degrees. So the 4 degree water sinks to the bottom. And on top of that is a 3, and then the 2, and then the 1. And then on top of that is the ice, which means that the ice has to freeze from the top down. So if that did not happen, then we would have ice forming at the bottom of a lake. And it would just freeze from the bottom up. And you may never actually get the bottom of the lake to thaw in the middle of the summer for some of the colder lakes, because the coldest water would always be at the bottom. But what's cool is that it's always 4 degrees at the bottom in the winter for these poor little fishies. And the whole lake has to freeze before the bottom gets warmer than 4. Or, it has to work its way down. Does that make sense? Okay. All right. Heat. So heat always is going to go from the warmer thing to the cooler thing. And so, wish me luck. I made an animation type thing. Are you guys ready? I made a lot of Google slides. So when you look at this presentation, you're going to be like, oh my goodness. Okay, so hot gases move fast. Okay, now if I let them mix, now you'll see them transfer some of their energy to the other ones. Yes? Did you see that? Okay. You cannot steal energy. Like the cold thing doesn't take energy away. It's the hot thing gives some of its energy to the cold thing. You can think of it kind of like money. If you don't have any money, you can't get any money. The only way you can get money is from somebody else giving it to you. Heat is the same way. It always goes from the one that has it to the one that doesn't have it. The person with money or with heat is going to give it to the person without money or heat. And so that is going to be this. So heat is the amount of energy that you can transfer. Now, you cannot give away more than what will make you guys equal. So it depends on your temperature difference. For example, if I have a cup of boiling water sitting on my table, it can give heat away to the room, but it can't get colder than the room. That would be ridiculous. Mass is going to matter. Like if I have a bigger thing, of course, it's going to have more energy to give away. And specific heat capacity. So if you've ever noticed, if you ever touch aluminum foil, like at a campfire or something like that, aluminum foil itself has a very low specific heat capacity. Whereas aluminum, 9 times 10 to the 2. Water is, so this is, why does it do that? Why doesn't it just say 900? Anyways, this is 900. Water is 4,186. So there's like 4 times more heat that the same amount of aluminum foil can hold versus water. So if you touch aluminum foil, it doesn't hurt that bad. It doesn't hold very much energy per kilogram. If you touch water, that hurts. You can burn yourself a lot easier. I mean, yes, you can burn yourself either way, but if you ever notice, aluminum foil is not nearly as bad as other stuff. So yeah, I need to look back at this. There's something that looks wrong about this to me. Anyhow, so you don't need to memorize these things. You just need to look at them in your textbook if you need them, or they will be given to you in the problem for those specific heat capacities. And then this is your equation. So Q is heat. It's not H, it's Q. I know, but it makes no sense. M is mass. C is specific heat. And delta T is your change in temperature. You will hear this equation referred to as Q equals MCAT, because the delta looks like an A. So Q equals MCAT. So the way that you'll approach these problems is the heat that one thing gains is going to be equal to the heat that the other thing gives away. Okay. So you can't just gain or lose energy from anywhere randomly. The amount of energy that one thing gains has to be equal to how much the other one loses. So you can make MCAT of one thing equal to MCAT of the other thing. Does that make sense? Okay. And change in temperature is always going to be final minus initial. A lot of times you'll have these problems where you're given the initial temperature of a block of iron and a block of water. And then you want to know what the final temperature is for both. And so you'll just do temperature final minus initial instead of the delta T, and then you can solve for the other. Does that make sense?